All right, welcome back everyone. We are going to spend this video introducing another common discrete probability distribution, and that is the hypergeometric distribution. Um, but before we do that, I will just make a quick note that the negative binomial distribution that we will cover in class, this distribution is actually more similar to the geometric. And so it has the word binomial in it, which is a little confusing in that it's not really that similar to the binomial distribution. It's a lot more similar to the geometric. And then the hypergeometric distribution is more similar to the binomial. And so again, it's really not similar at all to the geometric distribution. It's more similar to the binomial, as we will see in a moment. The naming of these two feels, unnecessarily cruel, but it is what it is, and we can't change the names. So again, we're skipping over the negative binomial. We'll do that in class and going straight into this hypergeometric. And we're going to consider this setting. So we've got this shipper that has a supply of 144 apples. She selects 15 apples at random. And we also have this other piece of information that there are 10 defective apples in the supply of 144. And so we're letting y be a random variable for the number of defective apples in the sample of 15. So before we look at the actual distribution function, we'll think about this first question. So why is the random variable y? Why is this not a binomial random variable? So it sounds like pretty similar. It's the number of defective apples in a sample. Why is this not binomial? And so to answer this, suppose that we choose this first apple. So it's the first of our sample of 15. The probability that this first apple is defective is 10 out of 144. So 10 defective apples, 144 total. If it's selected at random, that is the probability that it's defective. And so then suppose this first apple is defective. Then the probability of the second apple so now you're choosing another apple. What's the probability that that second apple is defective? Well, the first one was defective, and so that means there's only 9 defective apples left, and there's only 143 apples total. And so what you'll notice here is I'm going to scroll back up to the binomial experiment conditions. What you'll notice is that a couple of these are violated. And so both 3 and 4 you could think about as being a violation. So we're seeing our probability of success change from trial to trial, and the trials are also not independent because whether or not this first apple is defective affects the probability that the second apple will be defective. So we'll write a little bit of that down. So this violates the independence of trials assumption. And violates the assumption that P is the same in all trials. One other way that you could think about this is, so this would be a binomial random variable. If what? So this would be a binomial random variable if we sampled the apples with replacement. So if we sampled an apple, looked at whether it was defective, and then put it back, if that was a possibility, then this would be a binomial random variable because now p is the same from trial to trial and we have independence of trials. Okay, so we've talked a little bit about what a hypergeometric random variable is. This text formalizes some of what we discussed, and it also gives this probability distribution function. And so we've got capital N elements, and so I'll put this in context of our example. So there were 144 total apples. N is our sample size, so the shipper had selected 15 apples to sample, so our lowercase n is 15. And then R is the number of successes. And so we're thinking about a success as the apple being defective. And so there were 10 defective apples. And so R is equal to 10. We could also make sense of some of the pieces of this probability distribution function. And so this capital N choose lowercase n on the denominator, that is the number of ways to pick n items from n, capital N, available items. This piece on the right that I have just circled, that top part is the number of ways to pick lowercase n minus y items from the capital N minus R failures. So there are 134 apples that are not defective. These are the failures. And capital N minus R choose lowercase n minus y as the number of ways to select those n minus y failures. The last piece is similar in that this would be the number of ways to pick y items from a group of R successes. And so then the numerator also uses that mn rule to multiply those two quantities together. The final little pieces that we have these restrictions here. So y has to be less than or equal to r. That makes intuitive sense because the number of successes in our sample cannot be more than the number of successes in the population. And a similar logic follows for the number of failures. So lowercase n minus y, that's the number of failures in our sample. That cannot be more than the number of failures in the population. Okay, so coming back to our example, we've got this shipping example. So y is a hypergeometric random variable, and r is equal to 10. N minus r is equal to 144 minus 10, and lowercase n is equal to 15. So that is the way this hypergeometric distribution is parameterized. And then we could use this to figure out, for example, the probability that there are exactly 5 defective apples in the sample of 15. So probability that y is equal to 5. We could just plug in 5 for y. And this is kind of a pain to calculate by hand, but I think we've used these R functions enough now that you might be able to reason through that if we want to actually figure this out in R, there is a d hyper function, and d hyper will take our value of y, so that goes there. And then it will take the 3 parameters from the hypergeometric distribution as we wrote them out earlier. So 10, 144 minus 10, 15, and that is 0.00107 if you actually run that in R. We'll do one more quick example. So suppose that you wanted to find the probability that y is less than or equal to 2. So that the number of defective apples is either 0 or 1 or 2 in the sample. Then again in R, this would be p hyper and again the 2 gets mapped from there, and then the rest of the parameters are the same. So still 10, 144 minus 10, and 15. Plugging that into R will give you a probability of 0.929, indicating a very high probability that there will be 2 or fewer defective apples.